Hey, Ms. Stewart, how you doing?
I'm great, Mr.
This is my first digital electronics video.
This is so exciting.
very
I'm
exciting.
honored to be here.
So this is a circuit, and I'm just going to do a few calculations. This is a series circuit. There's only one path for the electrons to go, obviously. The electrons are leaving the battery. This is my battery. They're going through a couple of resistors, and then they go back home. So I'm just going to calculate a bunch of things. I'm going to calculate the total resistance, the total current. I stands for current, remember, and the voltage drop across both resistors. So we'll just go for it?
Let's go for it.
Let's go for it.
Have
Okay.
fun.
So here's my 10-volt battery. Again, imagine electrons are leaving the battery and they're losing some of their voltage as they pass across each resistor. The first thing I'm going to do, though, is I'm going to calculate the total resistance. Now, Ms. Stewart, that's pretty straightforward in a series circuit.
Good.
Total resistance, what do you think it is? Well, it's just the sum of both resistors. So I'm just going to add them both up. 30 ohms and 20 ohms. Total resistance is 50 ohms.
I think I could have
Yeah, you
figured
think
that
you
out.
can handle that? It's going to get a little bit more complicated when we do a parallel circuit. But
That's the
there it is.
total resistance.
So that is the total resistance.
Got
R
it.
sub T is total resistance.
Beautiful.
I'm going to calculate the total current. You only know one equation, right? Just one equation. The only equation you know is Ohm's law. V equals IR. That's it. Voltage equals current times resistance. I have two of the things that I need. I have the total voltage. It's a 10-volt battery. I'm looking for current.
Wonderful.
And I have the total resistance. I just calculated it. You just
Yeah.
add up the resistors.
Fantastic.
So I'm trying to get I. I'm going to divide both sides by 50.
A little algebra.
By 50. There you go. That's 10 over 50 or 0.2. I think I can do that one in my head.
Yeah.
It's 1/5 or 0.2.
0.2.
0.2. So
No calculator
I equals
necessary.
0.2. And the units, of course, is amps. This is current. So I'll put 0.2 amps. Now, if I ask you to write this in engineering notation, you have to have something in front of the decimal point here. So I would have to move this over, and maybe I'll squeeze that in here. I'll move it over 3 places. So it's 200, right? It was there, 1, 2, 3. It's really 200 milliamps.
Ah,
That's
interesting.
really how I should write it if I were to do it in engineering notation, which is what they want you to do sometimes. All right.
Yeah.
So let's calculate the voltage drop across both resistors now. Shall we
Okay.
do that?
Let's do it.
Well, how many equations do you know? You only know one equation. This
Ohm's
is
law.
Ohm's law. That's the only equation you know. So I'm just going to look at it in terms of each resistor. Again, V equals IR.
Good old Ohm.
I want to know the voltage drop, V. The current, well, I just calculated current. It's 200 milliamps. That tells me that there are 200 milliamps of current going through this circuit. There's no branches in this circuit, so that current must be the same every single place in the circuit. There's no place for the electrons to branch off. So that must be, I'm going to use 0.2 in my calculation, and we can convert it back in the end. So it's 0.2 times the resistance is 30. 0.2 times 30 is it 6?
It is 6.
Yeah, okay, I have to do it in my head there.
Yeah.
Thank you. It is 6, and I am calculating voltage. 6 volts.
6
Okay.
volts.
The voltage across R1 is 6. Let's do the same thing for the voltage across resistor 2.
Okay.
I guess I'm calling this resistor 2.
All right.
Hey, you only know one equation.
Ohm's law.
V equals IR. I'm looking for voltage. I know the current, it's the same going through here as 0.2. This time it's a 20 ohm resistor. 0.2 times 20 is 4. Did I do that right? Thank you.
You did?
That is 4, and again it is my voltage drop, 4 volts. I don't think I put volts here, did I?
You didn't, but that's okay. You can do it now.
Okay,
So
4
we-
volts.
4 volts.
And I've calculated everything I set out to calculate, and of course, you should be able to look at the end and say, you know what, this has got to be right. Why does this have to be right, Ms. Stewart?
Well,
Oh, please, go ahead.
let's see. I don't know. You tell
Well,
me.
okay,
I'm
so-
sure you can add stuff up.
Yes, you can add stuff up. So this is a 10-volt battery, which really means each electron that leaves my battery has 10 volts of potential energy. And you know, by the time that electron goes back home, here's the electron, he's going through the circuit, la 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 la. By the time he goes back home, he has to lose all of his energy. Well, how many volts of energy did he drop going across this resistor?
6.
6. How many did he drop going through this resistor?
4.
Which is, in fact, a total of 10 volts of energy drop, right? So the voltage drop must be equal to the voltage produced by the battery.
That
And there
is
you have
so fabulous. I love it.
Thanks. This is a parallel circuit, and I'm going to do some calculations with this.
Very nice.
So here I have my 20-volt battery, and I have 2 resistors, and they are wired in parallel. There's more than one loop for the electrons to flow, if you want to think about it that way, right? I mean, some of the electrons, as they leave the battery, some of the electrons might flow up this path. Some of the electrons are going to flow up that path.
I wonder how they came up with the name parallel.
Yeah, maybe. Thanks, Ms. Stewart. That's good. So we're just going to plunge right in, and I'm going to calculate these things about the circuit. I'm going to calculate the total resistance first, and then I'm going to do the current at these various places. Total current, and then the current flowing through each of these branches of my circuit.
Nice.
So, yeah, this is the funny one. When I calculate total resistance in a series circuit, I just add up the resistors. Oh, if that were only the case in a parallel. It's a little bit more complicated than that. We talked about this in class, but it turns out that the total resistance is equal to 1 over each resistor.
Yes.
So it would be like 1 over R1, I'm calling this resistor R1, plus 1 over R2. And it sort of makes sense intuitively that as I add more resistors in parallel, I could add another branch here, a resistor, the total amount of resistance of this circuit actually goes down. Because even though I'm adding another resistor, I'm creating another path for electrons to flow. So the total current is actually going to increase, which means that there has to be less total resistance. It's a little weird.
That is weird.
Yeah, but that's the law.
But that's
That's
cool.
how it works. So we're going to go through this crazy thing, and I think it'll make sense. So, can you still see me over here?
I
I'm
can.
going to calculate total resistance. It is just 1 over this guy, 1 over 5, plus 1 over 10. Obviously, if I had another resistor, it would be plus 1 over that, plus 1 over that. I mean, you would keep going. And you can do this with more than 2 resistors, you know what I'm saying?
Oh my gosh, crazy.
You can actually just punch this thing into your calculator really as is, especially if you have the fraction thing.
Right.
I usually punch it and I put parentheses there. 1 over 5 plus 1 over 10. Miss Stewart is doing it behind the camera.
This is so exciting.
It's very exciting.
What form would you like it in?
Give me a decimal. Give me a decimal. That's great.
It's 3.3 repeating. Also,
3.3 repeating.
Also known as 10/3.
Okay, let's do. I'm gonna go 3.33, and this is ohms. Calculating it in terms of ohms. Yeah.
Yeah.
That's good. That's my total resistance.
Very nice.
I didn't give myself very much space here. I'm now going to get the total current. How am I going to get the total current? We only know one equation.
Ohm's law.
That's the only equation you know. It really goes far though, doesn't it?
It does.
V equals IR. Well, it's a 20-volt battery.
Okay, that's my V.
I don't know the current. That's what I'm looking for.
But you know your R.
I do know resistance. That is 3.33, and of course I'm going to divide both sides by 3.33 to get I by itself, 3.33. I don't know, can you do that for me? That is
I think I
6
can.
or something like that?
Yeah, 6. It's actually going to be 6 exactly if I do
If you carry this more
3.3.
places.
Yeah,
Okay,
repeating.
I'm going to put 6. How's that?
I like it.
My total current is 6 amps. Terrific.
Beautiful.
So now I'm going to calculate the current through each branch of this circuit. Now when I say total current, of course, I'm talking about the current flowing out of the battery. In other words, there's 6 amps flowing out of the battery here.
Gotcha.
If if this was a series circuit, in other words, only one path for the electrons to flow, it would be 6 amps every single place.
Right.
This is a measure of how many electrons are flowing. Here in a parallel circuit, of course, some of the electrons are going to flow this way. Some of the electrons are going to flow that way. Interesting. So let's calculate how many electrons are flowing in each branch, the current in each branch. Hey, I only know one law. One
Ohm's
equation,
law.
I should say.
Yeah.
Thanks. Okay, that equation, V equals IR. Again, I'm looking for current here. I know R, but what's V? Well, it turns out that V, and you know this from class, that the voltage drop across this resistor must be 20 volts. And the reason, of course, for that is that every electron that leaves the battery with 20 volts of energy must lose all of its energy by the time it gets back home. So if it goes this way, it will drop all of its energy going through this resistor. If it goes through this branch, it'll lose all of its voltage or all of its energy going through this resistor. It's a 20-volt drop either way it goes.
Either way it goes.
Either way it goes. It has to lose all of its energy by the time it gets back home.
Interesting.
You know what I mean by back home?
I do.
In
Like
the other
back
side?
at
Yes,
the
back,
beginning,
that's what I'm saying.
when it finishes its little cycle.
I'm just going to fill that in. 20 volts. 20 volts. Can you see that's a 20? Or is that like messy?
No, that looks good.
Okay. So V equals IR. 20 equals, I don't know what I is, but I know that, I know that the resistance is 5. So
That was
20
given.
divided by 5.
4.
I think that's 4. Okay. So 4 is my current going through this resistor.
And you're calling that your first resistor.
That is correct. 4 amps. I'm just going to do the same thing over here. You only know one equation, V equals IR. The voltage drop I know is 20. I'm looking for current. Resistance is 10. Divide both sides by 10, and it 2, I think. Yes. So 2 amps. And of course, this should make total sense. When you're done, you should be like, oh yes, of course this makes sense. I have 6 amps of current. This is really like a measure of how many electrons are flowing. If I have 6 amps of electrons flowing through here, some are flowing this way, some are flowing this way. What did I say? 4 are going this way? 2 amps worth?
Right.
Can I say amps worth?
Yep.
Well, it makes sense that it has to add up to 6.
Yes, because that's your total.
That's the total. And when it comes back around the other side, going this way, I have to, of course, have 6 amps again, because I have my 2 amps and 4 amps, adds up to 6 amps. And there you go. That wasn't bad at all.
Not bad at all.
Thanks very much, Ms. Stewart.
My pleasure.